Lecture 2 of Unit 1 deals with the second part of the atomic theory. The first thing in this lecture is talking about waves, and there are two components of every wave. Wavelength, which is the distance between one crest to another, or one trough to the trough of another wave. The second component of a wave is the frequency, and as we see here, frequency is the number of times a wave repeats itself per second. In order to find the frequency or wavelength of a wave, we use the equation stated here. And what these symbols represent is c is equal to the speed of light, which is 3.00 times 10 to the 8th meters per second. Wavelength, which is identified by this symbol, is measured in meters. And then frequency, identified by this symbol, which looks like a V, is in s to the -1 or in hertz. They both mean the same thing. So here we have a practice problem which says find the frequency of a yellow light with a wavelength of 565 nanometers. So if we look at our spectrum of light, we notice that the visible light is toward the middle of the spectrum in this area right here. And we also note that frequency increases this way along the spectrum, and wavelength increases going this way. So based on this information, we can assume that yellow is going to have a somewhat high frequency. So to start off, we use our equation from the previous slide, C equals wavelength times frequency. But since we're trying to find the frequency, we have to manipulate this equation and isolate frequency. And we do that by dividing the speed of light by wavelength. So our equation looks like this. And now we just have to plug in our values. So C we know to be 3.00 times 10 to the 8th meters per second. And we were given our wavelength of 565 nanometers. But as we know, wavelength is measured in meters, so we must convert this into meters. Nanometers means that our exponent is going to be 9, and nanometers are smaller than meters, so we end up with 565 times 10 to the -9th meters. And when we plug this into our calculator, we find the frequency to be 5.31 times 10 to the 14 seconds to the -1st. The next thing we're going to talk about is the quantum theory, which was proposed by Planck, and he said that energy emitted from heated objects is emitted in units known as quanta, and that energy increases one quantum at a time. It doesn't skip a quantum or only increase half a quantum. It either increases a full quantum or not at all. And he also determined that the magnitude of a quantum depends on the frequency of the electromagnetic radiation being applied. And since the magnitude depends on the frequency, we can also infer that as frequency increases, then the energy per quantum will increase as well. And this is our equation to calculate the energy per quantum. So as we see, E is energy per quantum measured in joules. H is Planck's constant, which is 6.63 times 10 to the -34 joules per second. And as we know, this symbol is our frequency, which is measured in seconds to the negative first. And just like with our previous equation, we can manipulate it so that if we were given the E and were asked to find V, we could divide by Planck's constant and end up with V equals E over H to solve for the frequency. The photoelectric effect states that if a metal surface is hit with the correct frequency of a light, it will eject electrons immediately. And what it means by correct frequency is that every metal has a frequency threshold, which is a specific frequency at which it will eject electrons. What's important here is that a metal will not eject electrons until the frequency threshold is met, even if it's exposed to a frequency for an extended period of time. If it's not the frequency threshold or above, the metal will not eject electrons. Another key point is that once the frequency threshold is met, electrons are ejected immediately. It does not take any time for them to be removed. Increasing the intensity of light at the frequency threshold will increase the rate of ejection. So basically saying if we apply a greater amount of a light at the frequency threshold, then the electrons will be ejected at a faster rate. But it's important to know that all the electrons are traveling at the same speed or velocity. Just because we intensify the light doesn't mean that the electrons will be traveling at a slower or faster speed. And here Einstein's theory sort of sums the photoelectric effect up by using the same equation as the quantum theory of Planck, but instead of it being the energy of one quantum, it's the energy of a photon. And by doing this, we can directly relate quantum to a photon. So Einstein's theory basically summarizes that if the frequency is below the threshold, that no electron will be released, even if it's exposed for an extended period of time. And if the frequency is at or exceeds the threshold, the electron will absorb the energy of the photon, and the attractive forces holding the electron to the metal will break, and that is how the electron is ejected. So now we have Coulomb's law and the shielding effect. And Coulomb's law, which is this equation, F equals K times Q1 Q2 over D to the second power, is basically the equation of attraction. So F is equal to the force of attraction, K is a constant, the Q's are the magnitudes of charged particles, so whether it be positive or negative, and D is the distance between these charged particles. And this goes hand in hand with shielding, because as we see under shielding, it says that electrons further away from the nucleus are less attracted to the protons in the nucleus. Therefore, if we go back to Coulomb's law, this correlates because if we increase the value of D, that would result in a smaller value for F. So this makes sense, saying that as we increase distance, the force of attraction becomes smaller and less powerful. And as we see in our point here, the force of attraction decreases as distance increases. The same goes vice versa. If distance decreases, then we have stronger force of attraction because the electrons are closer to the positively charged protons in the nucleus. First ionization energy refers to the minimal amount of energy needed to remove an electron from the outermost shell of an atom in the gas phase. And ionization is always endothermic because it is the amount of energy needed, meaning that energy is being applied to the atom in order for the electron to be removed. So ionization is always going to have a positive value. The periodic trend for ionization energy is that it increases going up a group and increases going across a period. This is because force or energy, in this case ionization energy, increases as charges increase or become more positive and as distance decreases. So if we look at our periodic table, we know that group 1 has +1 charge, +2, +3, plus or minus 4, -3, -2, -1, and then 0 for the noble gases. However, this trend is not solely based on the charges, but more so on the shielding effect that we just talked about, because going across a period and down a group, you add more shells, which increases the distance of the electrons in the valence shell from the nucleus, providing more shielding and decreasing the attraction between that electron and the positively charged protons in the nucleus. So if that attraction isn't as strong, it won't take as much energy to remove that electron. Now we have the photoelectron spectrum, which determines the kinetic energy of the ejected electron. It records its frequency and determines the ionization energy. And we can determine the ionization energy using this equation, or as with the other equations, we can manipulate it if we wanted to find the Ke by adding Ke to the other side and then subtracting IE to end up with Ke equals HV minus IE. So depending on what you're given, you could use 1. So here's an example of the photoelectron spectrum of beryllium and boron. And if we take a look at our periodic table, we see that beryllium and boron are both in the same period, period 2, but beryllium's electronic configuration ends in 2s2, whereas boron's ends in 2p1. And this addition of a p subshell orbital is what causes the photoelectric spectrum of beryllium and boron to differ. But what's important to note is that when looking at this graph, we see that the ionization energy for that single electron in boron's 2p1 orbital is less than the ionization energy for the electrons in beryllium's 2s2 orbital. And this is because s subshells hold 2 electrons, and p subshells can hold up to 6. So the s subshell is full, it's at its max, and it doesn't want to lose an electron. So it's going to take more energy for beryllium to lose that 1 electron. Whereas boron, its valence orbital is p, which holds up to 6 electrons. And since it's only full with 1, it's really wanting to get rid of that so that it can become stable at 2s2. And that is one of the main reasons for the difference in ionization energies for the electrons in their valence shells. And just a quick highlight based on this PES graph. The force or energy increases as charges increase or become more positive and as distance decreases. So the closer an electron is to the positively charged protons in the nucleus, the greater the attraction because of Coulomb's law, as we looked at, and the more amount of ionization energy is needed to remove that electron. And as more subshells are added, ionization energy increases due to the shielding effect. And that is lecture 2 of unit 1.
So for the next lecture, we have lecture 4 on nomenclature. The first section on this lecture is all about naming binary ionic compounds. So the word binary actually means two. In this case, the two represents the metal and nonmetal that are present in the compound. And as we'll see, the metal will always be first in the compound, followed by the nonmetal. The metal will always also contain the positive charge, and the nonmetal will contain the negative charge. The positive charge is called a cation, actually, and the nonmetal will be called the anion. So in this example, we can identify both of the elements as calcium and phosphorus. As we can see in this case, calcium would actually be the metal, and phosphorus the nonmetal. So in this case, as we'll see, we have already separated the two elements and identified them. So now what we have to do is cross over the numbers from the bottom to the top in order to get the charges. And we'll see that calcium will stay with the 2 and phosphorus will start with 3. So as we talked about, the metal will always come first and be the cation, and the nonmetal will always come after and be the anion, giving them positive and negative charges as correspond. So after we have checked in the periodic table that the charges match, as they do here, we will name the compound, in which the metal's name will stay the same, so we will always have calcium. And then the anion's name, which is the nonmetals, would actually change to phosphide. As you can notice, we have added the ending IDE. So that is the basics on how to name binary ionic compounds. So just a quick run through again with another example. We could use AlBr3, which is actually, we can name aluminum as the metal, and we can name bromine as the nonmetal. So as we know, we should switch the numbers from the bottom to get the charges of each one of them. And Br will take the charge of 1, since here there is an imaginary 1 under the aluminum. The 3 in the aluminum would take the positive charge, and the 1 will take the negative charge. And then when naming them, we'll use the same rule, where aluminum will actually keep its name as aluminum, and this element will take the ending of IDE, making it aluminum bromide. One important fact to take in consideration is when dealing with certain transition metals. So most transition metal ions and a few other metal ions include a Roman numeral after their name. For example, we could have copper 2 or iron 3 when forming the compounds. This is because these metals form ions with varying charges, and the Roman numeral identifies the charges in each case. One example is the compound CuBr. In this case, bromide always has to be -1 because it is in group 7A, and therefore it will gain 1 electron. So in order to make this compound neutral, the copper must lose 1 electron, making this copper 1 bromide. So for the next section of the lecture, we have naming compounds with polyatomic ions. In this section, there are not a lot of rules for naming polyatomic ions, as names should be memorized. As shown in these picture, these are some common polyatomic ions. So, polyatomic ions where oxygen is combined with another nonmetal are called oxoanions and can be named systematically. This chart is a help for naming the oxon ions systematically. So, as this chart we can see on the right goes down, it means an increase in the oxygen atoms. One good example that we have is SO3, 2 negative, and SO4, 2 negative. As we can see, in sulfate, this one right here, there are 4 oxygen atoms, but in sulfite, we can see there are 3 oxygen atoms, showing how as the chart, you go down in the chart, the oxygen atoms increase. So in order to use this chart properly, you would add this beginning, insert the element's name, and then add this ending. And same here, the element's name, the element's name, the element's name, the ends, and only the first and the last would have different beginnings. So the next section would be to write ionic formulas. In order to write ionic formulas, first we have to identify our chemical name. So our example today will be magnesium chloride. So the first step would be to find magnesium and chlorine in the periodic table. So when looking at the periodic table, we're looking for the charges of each element. So in this case, magnesium in the periodic table will always have a charge of +2, and chlorine will always have a charge of -1. After finding the charges, we will use the crisscross method, opposite from what we used when naming binary compounds. So in order to find the formula, we would get the Mg and a subscript of 1 that we will not write, and Cl2 will take on, as I mentioned, the 2. This would then be the final formula by using the charges of each element. So when dealing with Roman numerals as we have here, iron 3 sulfate, we know that iron ion carries a charge of 3 plus by this Roman numeral, and also the sulfate written as SO4 carries a charge of 2 negative, since we learned our polyatomics. So we're writing the formulas. First we can write iron as having 3 plus, and sulfate as having 2 negative. We have to recognize that these are the charges that will have to be crisscrossed to give us Fe2, and in parentheses SO4 3. We will use the parentheses in order to recognize this as our polyatomic and this as our other subscript, and to also recognize that there are 3 sulfurs and 12 oxygens. So in order to name binary covalent compounds, we will have a list of prefixes in which the first word would take the name of the element with the suitable prefix, and the second word would take the name of the element with the IDE suffix and the suitable prefix. So as we can see, the list of prefixes is on the left side. For 1 we have mono, 2 di, for 3 tri, 4 is tetra, 5 is penta, 6 is hexa, 7 is hepta, 8 is octa, 9 is nona, and 10 is deca. So in order to further understand these, we have 3 examples. The one rule when naming them is that the prefix mono for 1 is not used where there is only 1 atom in the first element. So that takes place in our first example. We will not put mononitrogen since it is the first name. It will just be named nitrogen, but the second name for oxygen will take the prefix monoxide. Now for the second example, we do have a 2 which would take on di and add the word nitrogen right next to it. And for the oxygen we have 5, so it would be pentaoxide. For our third example, we have iodine and fluorine. So it would be iodine, not taking on mono since it is the first name. Add the prefix hepta for heptafluoride. Next up will be naming oxygen-containing acids. In order to name all acids, we'll have to look at the anion, but oxygen-containing acids have polyatomic anions in them. So in order to name them, we have to write the name of the polyatomic anion, but change. So add if it ends in ate, 8, to ic, or change ite, the ending of ite, to os. After changing the endings, we will also add the word acid. So we have here two examples. The first one, we will identify the polyatomic, and if we see here, the polyatomic is actually perchlorate. Just like we saw before, the ate will be the ending changing. So we will have perchloric changing into ic and adding the word acid to it. For our second example, we see that our polyatomic is actually nitrite. The ending is ite, therefore changing it to nitrous, ous, and adding the word acid to it. Next, we have naming non-oxygen containing acids. Non-oxygen containing acids have either monoatomic or polyatomic anions. So in order to find their names, we have to write the name of the anion. In this case, we're going to substitute its ending of ide, ide, to the ending ic. Also, we would add the prefix hydro and add the word acid at the end as well. So here we have two examples. Our first example has the ion's name of cyanide. So in order to name this non-oxygen containing acid, like we said, we have to add the prefix of hydro, then the name, cyan here, change its ending to IC, hydrocyanic, and then add the word acid at the end, making this its full name. For our second example, we actually have bromide, in which we know we will change the ending of ide to the ending of ic. So we will have hydro as its prefix, bromic following that, and adding the word acid at the end, making hydrobromic acid its full name. And for our last section is actually writing formulas for hydrates. In this section, we will use rules that we have previously learned in order to write the formula for the ionic compound, and then we will add a dot and the correct number of waters taken from the prefix. So if we have an example of sodium sulfate decahydrate, we will know how to now write sodium sulfate, which will be Na2SO4. This will be taken in consideration after the crisscross method we have learned. Now, for the prefixes, we have deca here, and as we previously learned, deca means 10. And hydrate is actually water. To join these two, we will use a dot in between of them. And for our last example, we will write down barium chloride as BaCl2 from what we've learned. We see that di will mean 2, and hydrate again is H2O, and we will unite them with the dot in between them, making that its final name. Thank you, and good luck with Lecture 4.
Going back to basic chemistry, the most important unit of measurement you have to know is Avogadro's number. This is 6.022 times 10 to the 23rd moles. This number is equal to 1 mole and relates to electrons, atoms, ions, and molecules. Another important concept you have to know is how to find the molar mass of a compound. So in this case, in the example given, they ask you to find the molar mass of CO2. So you take the mass of carbon and add it to the mass of oxygen. If it asks you to find the molar mass of SO4, you first have to find the mass of S, and then you find the mass of O. Since O has a subscript of 4, that means it is there 4 times, which means you have to multiply the 16 by 4. This gives you 64, meaning that the mass of O4 is 64 AMU. Now to find the molar mass of SO4 together, you add 64 plus the 32 of S and get 96 grams of mole SO4. The next concept is converting grams to moles and moles to grams. In the example shown, it asks you to find the moles of NaCl for the amount given. You then have to divide that by the actual molar mass of NaCl. Since the molar mass of NaCl is also equal to a mole of NaCl, that is what you multiply. So when it asks you to find the number of moles of CO2 in 56 grams of CO2, you first put the amount given, which is 56 grams of CO2. You then multiply that by the mole of CO2, which is equal to the molar mass of CO2. This gives you 1.27 moles of CO2. Converting moles to grams is the same thing. You take the amount of moles given and multiply that by the molar mass of the compound over the mole of the compound. So in the example, it gives you that there are 19.3 grams of CO2. You know that CO2 has 44 grams, which is also equal to 1 mole of CO2. Therefore, the amount of grams in CO2 is 849.2. In the next concept, you are converting grams to molecules. This is the same as the one before because you put the amount given and you need to find the amount of moles. From there, you have to find the amount of molecules in that mole. So as you can see here, this is the amount given. You need to find first the amount of moles in H2O to find the amount of molecules in H2O. So in the example, they're asking you to find 36 grams pure sample water. So you put the amount given, which is 36 grams of H2O, and find the moles in H2O, which like we saw before is multiplying by 1 mole over the molar mass. This allows you to find the moles of H2O, which in this case would be 2 moles. From here, you have to find the amount of molecules in H2O. If you look back at the first slide, you will remember that molecules also refers to Avogadro's number. So you know that from here you have to multiply it by 6.022 times 10 to the 23rd over 1 mole because Avogadro's number equals 1 mole. This gives you 1.2 times 10 to the 24th molecules of H2O. Now moving on to limiting reactant problems. The limiting reactant, as it says here, is the reactant that is used up and limits how far the reaction will proceed. The excess reactant is the reactant that is left over when the reaction is complete. In other words, the limiting reactant is the smaller amount and the excess reactant is the larger amount. To find the limiting reactant, you first have to see if your equation is balanced. In this case, it is. Step 2 would be to find the moles each reactant would produce. To do this, you need to put the amount of grams given like we've done before. So let's start with carbon monoxide. You take the 230 grams of carbon monoxide given and convert that to moles. So the molar mass of carbon monoxide is 28, and which is equal to 1 mole. Therefore, there would be 8.2 moles of carbon monoxide. Then you do the same thing, but for the hydrogen gas. So it says that there are 36 grams of hydrogen gas, and you need to convert that to moles. So the molar mass of hydrogen gas is 2.0, which is equal to 1 mole of hydrogen gas. This gives you 18 moles of hydrogen gas. So as we said before, the limiting reactant is the one that has the least amount. So in this case, it would be the CO, since it is less than H2, and H2 would be the excess reactant. So now if a question were to ask you what mass of methanol can be produced, you already know the limiting reactant. So now you can find the mass of methanol, which is the CH3OH. To do this, you take the limiting reactant, which you found to be 8.2 moles of CO, and use it to find the amount of moles in methanol. This gives you 8.2 moles of CH3OH. From here, you use the moles of methanol to find the grams of methanol produced by the reactant. You take the amount given, which would be 8.2, and calculate that 1 mole of methanol is equal to 32 grams. So with this, you calculate that the mass of methanol produced by the reactants is 262.4 grams. The last concept of Lecture 15 is finding the percent yield. Percent yield is the actual yield over the theoretical yield times 100. Percent yield questions will generally look like the one below, where it asks you to suppose that only 150 grams of the methanol in the previous problem were produced. If you look back at the previous problem, you'll remember that we received 262.4 grams of methanol. In this problem, it's asking you to find the percent yield if only 150 grams of methanol were produced. So you put this into the percent yield formula, where the actual amount would be this one versus the theoretical yield, which is the one we found before, the 262.4. Therefore, your problem would be set up like this: 150 grams of CH3OH over the 262.4 grams of methanol found before. From here, you multiply it by 100 to find the percent, and find it to be 57.16%. So your percent yield would be 57.16. Moving on to Lecture 6, which is a continuation of Lecture 5, we start out with the concept of mass percent, or the percentage by mass of an element in a compound or a component in a substance. The formula to find mass percent is you take the number of atoms in an element times the element's atomic mass over the formula weight of a compound. All of this times 100. Suppose you were asked to find the mass percent of silver in silver chloride. Then find the mass percent of chlorine in silver chloride. So what you do first is you take the number of atoms of the element in silver chloride. So let's start out with finding the mass percent of silver. There is 1 atom of silver in silver chloride. So you'd put 1 Ag atom. Then you look to find the element's atomic mass, which is 107.87 AMU. All over the formula weight of the compound. So it would be 107.87 AMU, which is the mass of silver, plus the mass of chlorine, which is 35.5 AMU. This all gives you 107.87 over 143.37. From here, you multiply this by 100 to get 75.24%, which is the mass percent of silver and silver chloride. To calculate the mass percent of chlorine and silver chloride, you would do the same thing. So first, you would see that there's 1 atom of chlorine in silver chloride. So you would write 1 atom of chlorine. Then you multiply that by the molar mass of chlorine, which is 35.5 AMU, all over the entire formula weight, which you saw was 143.37. You take this and divide it by the formula weight and multiply it by 100 to get your percent. Therefore, your answer would be 24.76%. Now, as you can see, the percent of silver is 75.24 plus the percent of chlorine, which is 24.76, gives you 100%. The next concept is that of molecular and empirical formulas. A molecular formula is a chemical formula that provides the actual number of each type of atom in a molecule. The empirical formula is the chemical formulas that provide the relative number of each type of atom in a molecule. So in other words, the empirical formula is the simplified formula of the molecular formula. So first, we are going to start out with the empirical formula. There are 2 basic steps necessary to find the empirical formula for each compound. So step 1 is assume you have a 100-gram sample and convert each element into moles. Then you will divide the number of moles of each element by the smallest value for moles calculated in step 1. To practice this, we are going to suppose you are given a compound containing 25.3% magnesium, 35.6% sulfur, and 39.1% oxygen. What is the empirical formula for this compound? So going back, the first step is to assume you have a 100-gram sample and convert each element into moles. So let's start out with magnesium. By assuming we have a 100-gram sample, we make 25.3% into 25.3 grams in order to convert it to moles. Like before, we find the mass of magnesium, which is 24.3, and we see that that is equal to 1 mole of magnesium. Therefore, we find that there is 1.04 moles of magnesium. The next step is to find the moles of sulfur. So we see that there is 35.6%, and we make that 35.6 grams in order to convert it to moles. And that the mass of sulfur is 32.1, which is equal to 1 mole of sulfur. So we now see that there are 1.12 moles of sulfur. The last thing to do is find the moles in oxygen. So we see that oxygen has 39.1%, which is 39.1 grams, and we multiply that by 1 mole of oxygen, which is equal to the mass of oxygen, which is 16.0 grams. We get that there is 2.44 moles of oxygen. Now that step 1 is complete, we look back at our moles to see which one the smallest value is. As we can see, the smallest value would be that of magnesium, which is 1.04 moles of magnesium. Then we divide this value into all of the other values calculated in step 1. So, the value of magnesium, which is 1.04, is divided by the smallest value, which is also 1.04, and we get that it's 1. So, therefore, there is 1 atom of magnesium. Then we need to find the amount in the sulfur. So, since there is 1.112, we divide this value by the smallest value again, which is 1.04, and we round that to 1 of sulfur. The last thing we do is divide the amount of oxygen, which is 2.44 moles, divided by the smallest value, which is 1.04, and we get 2 of oxygen. Therefore, our empirical formula is MgO2s. To find the molecular formula, you will divide the molar mass of the compound by the empirical formula molar mass. Then you get a number, which is what you will multiply every number in the empirical formula by. So, suppose the molar mass of the compound in the previous example is 176.6 grams. Find the molecular formula. So, going back to the previous example, we see that our empirical formula is MgO2s. So now we take the molar mass, which is 176.6 grams, over the empirical formula mass, which is the mass of Mg plus the mass of O2 plus the mass of S. So, by looking at a periodic table, we see that the mass of Mg is 24.3, the mass of O, which is 16, times 2 is 32, and the mass of S is 32.1. All of this added together results in 88.3 grams. So now if we divide the molar mass of the compound by the empirical molar mass, we get 2. Now going back, we know that our empirical formula is MgO2s. So now that we found the multiplier for the empirical formula, and we know that it's 2, we have to multiply all of this by 2. Therefore, our molecular formula is Mg2O4s2. And these are the basic concepts for Lecture 6.